So good morning, everybody. Welcome back to this morning session. Today we start at 9. The good news is tomorrow we start at 9:30. Okay, so recall that my lecture was about the ice surface. And just to summarize, the main result of my previous lecture, there was some maths, but the main takeaway message of my previous lecture is that we have found that the ice surface at moderately high temperatures exhibits ice pre-melting. Okay, it exhibits ice pre-melting, but this is a kind of limited pre-melting in the sense that when you reach the triple point, it remains finite. It doesn't diverge. Okay? And why do we care about that? It's because we are trying to understand the complex morphology of ice crystals, and we conjecture that part of that complex morphology must be related to the complex structure of the ice surface, which, when you have pre-melting, is a state of large surface disorder. Okay? And if you have large surface disorder, perhaps you have more strange phenomena going on that could explain the unexpected crossover of the shape of ice crystals. Okay, so our goal is to understand these transitions here that occur at low saturation in the Nakaja diagram, and why do plates become columns, and columns become plates, and plates become columns as you cool down the temperature of the ice. Okay? So that's the conclusion of yesterday, but before I continue, I still need to meet a challenge that I skipped yesterday. The other day, on Monday, we've seen these pictures, but perhaps we didn't pay enough attention to them. Okay? Notice that this is a micrograph of the ice surface barely supersaturated. How can we tell it's barely supersaturated? It's because it's developing patterns. Those stripes are actually terraces in the crystal surface. At low temperatures, ordered crystals usually grow by spreading. Okay? You have an ice crystal with a flat surface, then some step forms, and this propagates horizontally. Okay? And that's what we're observing. So just by the mere fact that we are observing stripes, we know that we must be a little bit supersaturated. What does that mean in a phase diagram? Where are we? Say we are at this temperature. It means we are a little bit above the sublimation line. And then ice starts being more stable than the vapor, and so the vapor deposits on the ice surface, and the ice surface grows. Okay? That's what's going on. Eventually, if you increase the saturation, you get liquid droplets. Okay? What's then going on then? We increase saturation. So we must be above this point, indeed. But where about? Above this line. This is the metastable prolongation of the liquid-vapor coexistence. If we observe droplets, water vapor is condensing, so it must become also metastable with respect to the liquid phase. So now we are somewhere here. Okay? Still, we are in conditions of quasi-equilibrium. And quasi-equilibrium means that the chemical potential of the water molecules inside the droplet is equal to the chemical potential of the water molecules in the vapor phase. Okay? Then given that I have two states, two phases, water and vapor coexisting or appearing simultaneously, which one of them has the highest pressure? That we saw yesterday. At equality of chemical potential, it's always the phase that is most stable that has the largest pressure. Okay? So inside the droplet, we need to have larger pressure than outside. And that satisfies completely the Laplace equation. Okay? So it means that the pressure inside the droplet, there's the pressure outside the droplet, needs to be positive. Okay, so that's just as a little overview of the lecture. Now, we're not really concerned about the droplets for the time being. We're concerned about this surface. Because these authors are observing terraces. And terraces are typical of surfaces which are rather ordered. Okay? And the canonical model of growth from an ordered surface is you have a flat surface, you grow steps somehow. This is an activated process. And then molecules come here, and here, and here. So the steps spread horizontally. Okay? That's what the authors are seeing. It seems okay, but how is this consistent with this? The experimentalists who found this picture conjectured that this picture needs to be completely inconsistent with the hypothesis of premelting. So what they claimed is that because of this observation, you can rule out premelting. Okay, so I have this challenge to meet. You cannot just go about showing your own conclusions and ignoring the previous work. Okay, so we need to reply to this or something without an explanation. Okay, so this is the situation the experimentalists think they are seeing. Okay, it's some very smooth surface of ice, very ordered, therefore not consistent with premelting, which has developed a terrace and which grows horizontally. Okay, so the issue is as follows. Couldn't we have this other situation? This is what the authors think that we ought to have if there was premelting. And if this was the case, then we wouldn't see any steps because it's a microscopic image. It sees the surface. So they would see just the flat premelting surface. Okay? So it seems we can rule out premelting. But there is another alternative, isn't there? You could have this other alternative. Okay, so in watching physics, these two alternatives are well known. This is called a Hild surface, Hild. Okay, it has some bump, and the premelting film, the liquid film on top of it has healed the bump. This is an important concept in painting. You want paints to heal your imperfections on the surface. Okay, and this is the situation where the liquid film is actually obeying the dictates of the bump. Okay, so this is the healed state, and this is the what's the state? I don't remember the name now, but it's the one in which the film follows the pattern. Okay.
This is atomic force microscopy.
That's right. If you look with atomic microscopy to this state, you're going to see the step, only that you cannot tell that there's a liquid film on top of it.
But the way you do the imaging is based on the interaction between the probe and the surface. Cannot you imagine that the interaction between ice and the probe is much stronger than between the teeth and water, and so you just don't see the water?
No, it seems not from this technique. Okay, from this technique, it seems you cannot tell. And the authors acknowledge that you wouldn't be able to tell the difference from their technique.
Is this drawing more or less to scale in the sense that the height of the step is similar?
No, it's not.
To the thickness of the prement?
No, typically this psi is going to be much larger.
The B, I mean B in comparison to HE.
Yes. The equilibrium film thickness is about 2 to 3 times one elementary step. Okay, so it's of the same order of magnitude. So B is one elementary step. It's 1 unit cell high. Okay, and so here I am assuming a length of step with this psi and an elementary step of unit B. Okay, so in order to understand which of these two situations actually occurred in experiment, what we need to do is to calculate the free energies of such states. Okay, and I'm going to do this in a hand-waving kind of argument that very much resembles, I fancy, to what is often done in the French School of Physics. Okay, so let's first try to calculate what is the free energy cost of this Hild state. Okay, what is costing me free energy here? What is costing me free energy here is that usually I'd like to be at the equilibrium film thickness. But actually, along the path of the step, I am not at the equilibrium film thickness. Okay? So how do I account for that kind of free energy? That's precisely the role of the interface potential. Okay? So my free energy here is going to be the interface potential as a function of the film height. And the film height here is HE, the equilibrium value, plus some perturbation, multiplied by the length of the imperfection. Okay, so if I make a Taylor expansion, to second order, I will get this. Okay? But by definition, HE is the equilibrium film thickness. The equilibrium film thickness is that which minimizes the interface potential. So I can rule out this term. So the cost of having this imperfection is this term. Okay? This is my equation for the cost of healing the step. It's dictated by the second derivative of the interface potential, okay, and the length of the healed obstacle. Okay? What is the free energy here? Here, what I'm doing is to follow exactly the dictates of the interface potential. I am being at equilibrium film height everywhere, here and atop the step. So what costs me free energy here? That's right. It's creating the interface. Okay? And so how do I measure the amount of new interface that has been created? From the slope, from the average slope of this bump. Okay? And the average slope of this bump is here. It's just B, the step height, divided by the length of the obstacle, squared. Okay? That measures the amount of extra surface created. And it's weighted by the liquid vapor surface tension. Okay? It costs me this to create this bit of extra surface tension relative to the horizontal. It's given by this equation. It follows directly from the formula of the arc length, of an arc length. Okay. And now, which one is most expensive to follow? I just need to compare this free energy with this free energy. I equate the two free energies. Okay, go ahead.
Why is the square here? B opposite of square?
Because in the formula for the arc length, you have square root of 1 plus square derivative. That is what measures you the extra, so it's a square. It's not just the slope, it's the slope squared, okay?
So why do you multiply it again then by the length?
Because it occurs over, because it's the average slope. Okay, in the formula for calculating areas, if you're going to calculate your area, you say, what is the area of a curve? Okay, it's this formula. This will be a measure of the increase in slope integrated over the full range, where the slope is finite. Okay, and now you equate these two results, and you find that the surface will be healed only if the length of the imperfection is given by this distance. So that's the surface tension less the second derivative of the interface potential. Okay?
You put something for delta H, I guess. You put a value of delta H.
No, it cancels. Oh, something is missing here. Okay, delta H is actually something missing here. It's B likely.
It's H, you put it HE, I guess, in those cases.
There's something missing. Delta H should vanish. And so there's missing some delta H here.
Yeah, but also B is vanished, so delta H is B, no?
Likely yes.
Maybe something like that.
I'll need to take a look at this because it's something, there is some misprint here. Okay? But nevertheless, you introduce this concept, which is the healing distance. Okay? It's the ratio of a surface tension and a second derivative of the interface potential. And the conclusion is that whenever you have an obstacle in your surface of size L, which is smaller than a healing distance, then this obstacle will be healed. That is, the film will not adapt to it. And so you will see a perfectly smooth surface. If, on the other hand, your step is larger than the healing distance, the film is unable to heal that. And what it does is to adapt to the step. Okay? And from the surface tension value of water and my model of interface potentials, I calculate a healing distance of 1 nanometer. Okay? So let's go back to the experiment. This is the ruler they use. So these terraces are far larger than 1 nanometer. So they cannot be healed by a pre-melting film. So you can still have a pre-melting film. Okay, you can still have a pre-melting film and observe these steps in the experiments. Okay? So we're okay then. And we can now go to lecture 2, which is about the surface structure of the crystal and how does this affect the growth dynamics. Okay? So we solved this problem. At least we are consistent with having a pre-melting film. Huh? And our role now is to study in more depth the equilibrium structure, to describe the surface fluctuations. And why do I care about surface fluctuations? Because if I study surface fluctuations, and this is a general principle in physics, I always get information on the linear coefficients which dictate the out of equilibrium behavior. The close to out of equilibrium behavior. Those coefficients are always given within, are contained within the fluctuations that you observe in equilibrium. So that's a very good technique to study properties. Study your system at equilibrium where it's well behaved, calculate the fluctuations, and those fluctuations always convey you information on how the system is perturbed with an external source, okay? Without having to perturb it, which is always at some trouble. Okay, so the first thing we need to know about solid surfaces is a distinction that is not very well documented. You actually have two main types of solid surfaces. These kind of surfaces, which are sort of very flat and exhibit excitations in terms of elementary steps, the ones we've been talking about, are known in the literature as smooth surfaces. We're used to thinking of the surface of crystals always as smooth. Why? It's a cognitive bias. Okay? You can only get nice micrographs of almost atomic resolution with techniques that work in conditions of very low vapor pressure. And so we're used to seeing nice surfaces. When you increase the temperature, your vapor pressure is high, and then you have troubles making atomic resolution experiments, imaging of that. Okay? But at sufficiently high temperatures, or when the two faces are sufficiently alike, many times the solid surface is rough. There is no distinction in solid surfaces that are rough with an ordinary fluid interface. Okay? Of course, the viscosity is going to be much higher. But the structure, the static structure, is not distinguished from that of a liquid-liquid interface when you are rough. Okay? And this is not well known, but it's a very, very real situation. And the problem is typically you cannot make pictures of these situations. Most rough interfaces occur between a solid and a liquid, and you cannot image that very well. Or they can occur at a metal interface close to the triple point, where the vapor pressure is huge and you don't want to make experiments at 1200 Kelvin. Okay? So that's why they're not well documented experimentally. Now, why should we care about this distinction? It's really important because it dictates in a great deal the shape of the crystal. So this apparently sophisticated distinction has a macroscopic manifestation. If you are a smooth surface, the crystals grow with edges that are very pointy. So the typical nice crystals that we can see, they correspond to smooth surfaces. The crystals have pointy edges. Now, if you are rough, the points, the edges, the pointy edges disappear and they get rounded. Why is that? Because if you are a rough surface, you can deform easily. And you don't want pointy edges in principle in thermodynamics. You want uniform states. So you get a round crystal, okay? But we don't care that much about that here. What we care is that this distinction is also crucial for understanding the growth dynamics, okay? Smooth surfaces, as I described, they only grow by horizontal spreading of the terraces. That is a very slow activated process, because first you need to nucleate a terrace which is sufficiently large, and then it starts spreading. Otherwise, it's going to vanish. Right? And so these crystals grow by a slow activated process. It's two-dimensional nucleation. It's a slow dynamics. If, on the other hand, you are a rough interface, there are no privileged spots in your surface, and you have a nice, simple growth law. The rate of growth is linear in the saturation. So this is fast growth, this is very slow growth. Okay? So that's an important distinction. Now, how could we describe the difference between these two kinds of states? Here we're going to introduce a Hamiltonian, which is called the Sine-Gordon Hamiltonian. Okay? We call it Hamiltonian because of the analogy I described the other day, but actually it's a free energy. We want to measure the free energy of this surface, and we want to characterize how it fluctuates. Okay? So what we do is to introduce, by hand waving, a potential. This potential is completely invented. Just as I invented potentials the other day. The only important thing that you need to put into this potential is what you actually know that happens in your system. If you have a smooth surface, what you know is that the surface height needs to be congruent with the lattice spacing. It needs to be congruent with the lattice spacing. That's all you know about it. So you invent a minimal model for what is the propensity of the surface height to be. The propensity of the surface height is to always lie at the minimum of some potential that is sinusoidal. Okay? So the crystal doesn't care. The crystal lattice is uniform. It's made, say, of an array of atoms, and it doesn't care, the crystal lattice doesn't care whether you are here or you are here, or as a matter of fact, or you are here. As long as you are in a surface height which is congruent with the lattice spacing, the lattice is happy. Okay? So this term here, which is phenomenological, is meant to describe the propensity of the surface height to align with the lattice spacings. Okay? Now, because, of course, the lattice doesn't care whether you are here or here, but if you were initially at this state and suddenly you jump, here there is a penalty. There's a free energy penalty. So we are going to punish the formation of steps with a term here that is proportional in the squared slope. That is just as we do always. We have tendency for the system to be homogeneous. Whenever it's inhomogeneous, there's a slope. We blame the square of that slope, the free energy cost of doing the inhomogeneity. Okay? So that's called the Sine-Gordon Hamiltonian. And it's actually used in physics in very different systems. It's convenient here to describe this system. Okay? So this accounts for the cost of making steps, and this is asking the surface height to remain congruent with the lattice spacing. Okay? And now we want to solve this Hamiltonian. Yesterday, on Monday, we discussed how to solve things in situations. Recall that this is just like a Hamiltonian. This is our kinetic energy. This is our potential. Now it's a sinusoidal potential. We could solve this with the analogy of the Newton's equation, but then we would solve for just one single trajectory. That is one single realization of the film profile. And here we want to study the fluctuations. So we cannot use that trick. What we're going to do now is to try to find out what are the typical fluctuations of this crystal. And to do that, we make a second-order expansion of this cosine term about say, ground level at h equals 0. We set the surface height at 0 when it's perfectly smooth. And we ask ourselves, what would happen if you move away your film profile? H is this. How is this function? Okay. What will be your film profile fluctuations when they move away from the standard flat state, which is the low energy state? Okay. You make a Taylor expansion and you get this. And this is already a little bit nicer than this because it's quadratic. And in this kind of problems, there is a mathematical trick, is that whenever you see a Hamiltonian, a free energy that is quadratic in your order parameter, it's very convenient to introduce Fourier modes. Okay, so I describe my surface height fluctuations in terms of Fourier modes, replace the Fourier modes here, here and here, and then if you integrate about x, that's a good homework to do, you get a very nice simple expression for the free energy. Okay? The free energy appears to be a function that is quadratic on the Fourier modes. These are the amplitudes characterizing the surface fluctuations. It's quadratic in Fourier modes. Okay? And I have introduced this lattice free energy. It's related to U. Recall, U is an important parameter. It's the lattice free energy. How much it costs the surface height to jump from one step to the other. Okay? So that's my free energy, but this is the free energy for a given realization of a profile, for just one. For each collection of Fourier modes, I'll get a free energy. And in this way, I can measure what is the likelihood of getting one fluctuation or the other in my system. Okay? So if I want to solve the problem, I want to understand that this is one single realization of the surface profile, and actually, what is the probability of such a realization? It will be a Boltzmann weight. The probability of getting a given realization of Fourier modes of my surface is a Boltzmann weight. It's the exponential of the energy of that realization divided by kT. Okay? So that's a Boltzmann weight. But now I can compare this Boltzmann weight with a usual Gaussian function. A Gaussian function is an exponential of x squared, where x squared is my random variable. And here, this is playing the role of x squared. This is a squared form in the Fourier mode amplitudes. Okay? What does that mean? It means that the prefactor that goes in front of the squared Fourier modes is sigma, the inverse sigma. Is the mean squared amplitude. So this is right away takes me to this equation. I recognize what is sigma in this equation comparing to the Gaussian function, and I get an exact equation for the mean squared amplitude of the Fourier modes. For the mean square amplitude of the Fourier modes. Okay? That's actually an application of the equipartition theorem. Not for an ideal gas, for the Fourier modes of my surface fluctuations. Now, here I could have two different situations. Either my lattice parameter W is different from 0, which is what I will usually expect in a crystal. I have a crystal, therefore I have a lattice. So W is different from 0. And then the fluctuations need to be finite. They need to be finite. Why? Because these real space fluctuations are the sum of all these Fourier modes. So if I integrate this, I get a logarithmic function. And I will get that my fluctuations are finite. So that makes sense. If I have a flat crystal, it has small fluctuations. It can make one step up, one step low, perhaps two steps up, but at a macroscopic level, it looks finite. So when Q goes to 0, the amplitude of the fluctuations remain finite. That's a smooth surface. Okay? What happens if W were to become 0 for some unknown reason? If W is 0, okay, then when Q goes to 0, the amplitude of the Fourier modes diverge. It goes to infinity. So in rough surfaces, that's exactly the fingerprint of a rough surface. You have a rough surface it means that the amplitude of the surface fluctuations can become infinite. And it becomes larger and larger as the wave vector becomes smaller and smaller. Okay? That's exactly the fingerprint of a fluid interface. With a glancing angle X-ray spectroscopy, you can study the fluctuations of the surface, and you can get exactly this result. For fluid interfaces, W is equivalent to B0. Okay? So that's the way of distinguishing rough and smooth interfaces when you study surface fluctuations. Okay? And we will need to use that result. Okay? So now we have described two types of solid interfaces, smooth ones and rough ones, and now we know how to distinguish them by studying the surface fluctuations. And that's very convenient because it's something you can study in experiment. It's something I can study in computer simulations, and I will do so, just by studying the way the fluctuations of the surface height changes. Okay? Now, that's a distinction, but I haven't said how on earth could W become 0? If you have a crystal lattice, how on earth can W become 0? Recall that W is related to U, which is the parameter that tells me that I am a crystal. So how can U become 0 and U be in a crystal if U is telling you what? That you are a crystal just by having finite U. What's going on? What's the question? Okay? Perfect. So it's the lattice parameter. Okay? So how can that occur? To understand that, we need to go, perhaps, I presume it might be intuitive, to do a quantum analogy. It's strange to, but this behavior is so exotic that a quantum analogy is going to give us an intuitive view of what is going on. Yes?
Here you always assume that the surface can only grow, right? But in solid liquid interface, you have a constant attachment and detachment of atoms on the surface.
No, for the time being, I'm describing the equilibrium surface. Okay? The equilibrium surface. And then using linear response theory. Okay? The fluctuations of the equilibrium surface are going to give me hints on how you grow when you're out of equilibrium. Okay? So I have my Sine-Gordon Hamiltonian. Okay? My Sine-Gordon Hamiltonian. This Hamiltonian gives me the energy cost of a given realization of the surface disorder. I want to know the partition function. The partition function will be the Boltzmann factor of this weighted over all possible realizations of the surface disorder. That is, over all possible shapes of the surface height. Okay? The low temperature state is just a flat surface. But as I increase temperature, I can get all sorts of different realizations of the surface. For each realization of the surface, I have one function h. And for each such function, I put it into this Hamiltonian and I get the free energy cost. But now I need to measure the partition function because I want to deal with the fluctuations. So my partition function is going to be a Boltzmann factor weighted over all possible, this differential is a functional differential. I'm not integrating over the values of x. I'm integrating over all possible functions, h of x, that resemble a surface. Okay? That's my partition function. And perhaps some of you can recognize this object. It has exactly the same form of a path integral. So this is an alternative formulation of quantum mechanics. Never mind if you know that. The significant thing here is that calculating the surface fluctuations of my surface height is completely equivalent to calculating the quantum problem of particles moving in a periodic potential. Okay? I have a periodic potential, and I want to solve the quantum problem of many particles sitting here on this periodic potential. Yes?
So the thing in the exponential is the action.
That's right.
But I can't remember what the action is.
The action is, well, for our purposes, is this. So the action is like a Hamiltonian. Okay, it's a Hamiltonian. This is the kinetic energy part. Recall that the action is a classical action. The path integral becomes quantum because you integrate over all paths. The path that maximizes this thing would be the classical trajectory, okay?
But there's no KT in the quantum action.
Yes, it's here.
No, but in the quantum version.
Well, in the quantum version, it's some imaginary time.
It's h bar blah.
Yeah. Okay? So it's analogous to studying how electrons will distribute over this potential. Okay? So two things can happen. Look, this is the equivalent of the kinetic energy. So my surface tension is equivalent to a mass. If I am really massive, I behave classically. Okay? So at low temperature, my surface tension is large. So at low temperature, I'm going to behave classically in this analogy. So how is the distribution of the electrons going to be? It will be, a classical distribution. Okay? My distribution of electrons is going to be an arrow Gaussian centered in each of the minima of the potential. Okay? That's the expectation for a system that is classical. It's like being in a harmonic oscillator. Your distribution will be centered about the minimum of the potential. Okay? Now, if you increase the temperature, the surface tension decreases. This is like becoming less heavy, and you get closer to a quantum situation, and then your distribution is going to broaden. Still, the distributions are localized, but they are broadened. But if you decrease the temperature, the mass further on, then the distributions start to tunnel. They are tunneling. And eventually, at sufficiently low surface tension, that is sufficiently small mass, you become an electron. And you behave fully as in quantum mechanics. So this tunneling is going to result in the overlapping of each independent distribution, and then you get a uniform distribution. You get a uniform distribution of the probability of finding H, just as you get a uniform distribution of the probability of finding the electrons anywhere in the system, even though you are subject to a periodic potential. So electrons in a crystal are filling the nuclei, but they don't care. They are so light that they prefer to fluctuate and move around the whole crystal. So this roughening transition, this is the roughening transition. Okay? The transition in which eventually the localized distributions, which were telling me that I must obey congruent lattice spacings, eventually disappears, and the distribution of heights becomes uniform. And then I say I become rough. And that occurs at the roughening transition, which is very peculiar. It's only given by the surface tension and the lattice spacing. Okay? The energy parameter of the lattice doesn't appear anywhere. This is what is called a fluctuation-dominated transition. In fact, it's a Kosterlitz-Tools type of transition. Okay? So it's completely analogous to the transition between an insulator and a conducting material. Okay? If electrons were heavy, they would always be insulators. If they're sufficiently light, then you become a conductor. Okay? So that's the origin of the roughening transition. We can be a crystal, and because of fluctuation-dominated, rather sophisticated transition, we transform our smooth surface into a rough surface, which exactly the same properties as a fluid-fluid interface. Okay? This was worked out in the 80s, but it's not something that is widely spread known.
If you put numbers in your roughening transition temperature, what does it give?
It's not too bad, but you cannot expect it to be quantitative, because it's okay, but it's not far away from the orders of magnitude. Okay?
In your temperature of transition, you have the B term, and B is the vertical size of the...
Yeah, it's the lattice spacing.
So it's the lattice spacing. So is it the same as KZ?
The same as?
Is it the same as the inverse of, is the length wave you have put in W, in fact?
Yes, Kz, it's 2 pi divided by B. That's right, 2 pi divided by B, correct. Okay, so this is appealing. Why did I introduce this? It's sophisticated, but it's appealing. I'm saying, it's not well known, but that solid surfaces can undergo a transition, and that this transition completely changes the kinetics of the crystal growth. So it's very appealing to think that this kind of transition must have some resemblance with this change of habits in the crystals. So that's what I am introducing it. Okay, it's complex, but it might be worth considering. Okay, let's have that in mind. But this is a canonical transition to describe solids for people who have done it in this sophisticated way. But in the canonical description, it was done for systems in which the interface is simple. I didn't put any drawing of the pre-melting film in that transition. So when I found this transition, and I got excited that it could explain the Nakaya diagram, the problem that I encountered is that there was no mention of the pre-melting film, and it's not meant to describe this kind of already rather disordered surfaces. Okay, so yes.
Could you say again why, intuitively, why the surface tension would depend on temperature?
Yes. In a simple way, the surface tension is the cost of creating an interface. That is the cost that you have because you have two different phases. So as you increase the temperature, the phases become more and more alike. So it's a general principle that the surface tension decreases. The surface tension decreases with temperature. Okay? So if you were at a liquid vapor interface, that's easy to see. If you're at a liquid vapor interface, as you increase the temperature, surface tension goes down, and eventually at the critical point, it must vanish. Okay. My role is, I have studied this problem with no pre-melting, okay? And I know I can describe it with a sine-Gordon Hamiltonian, okay? But in fact, my situation is that I have some solid, and on top of the solid, I have a pre-melting film. And this pre-melting film will also be subject to fluctuations, okay? Now, how can I describe those fluctuations? Those fluctuations can be well described with a Hamiltonian that is known the capillary wave Hamiltonian, okay? I'm concerned about the fluctuations of the liquid vapor interface here that bounds my pre-melting film. And this is described in this very usual way. This is the interface potential, of course. It's going to say to the interface, you try to be at the equilibrium film thickness. That's what the interface potential says. That's its rule. But thermal energy is going to say, let's try fluctuations. And the fluctuations will be penalized by the amount of increase of the surface area. So again, I have this kinetic energy term, which accounts for the increase of the surface when the surface curves. Okay? It's a well-known Hamiltonian. And what I need to do is just to add them both up. So I want to describe my solid with a pre-melting film, and that is done by just summing both Hamiltonians. This is the sine-Gordon Hamiltonian. It will dictate how this fluctuation, how this surface fluctuates. And then I have the capillary Hamiltonian, which is going to describe how this surface fluctuates. So I have two surfaces. The ice surface is complex. I cannot describe it with one dividing surface. I need two. Okay? So this describes how this H fluctuates. This describes how this H fluctuates. But notice that I have the interface potential. And the interface potential is a function of the pre-melting film thickness. So via the interface potential, I couple both Hamiltonians. The film thickness is the difference between this surface height and this surface height. So I get this sine-Gordon plus capillary wave Hamiltonian, which looks complicated, but it can be solved in a similar way as I solved the other one. What I need to do is to expand this in a quadratic expansion. Do the quadratic expansion. Okay? And then I have a Gaussian. The only problem is that it's a multivariable Gaussian. But conceptually, it's the same thing. It's a Gaussian that depends on the squared variables, and my problem is that now the variables are two. So I have an x squared term, an x times y, a y times squared term, and each of such terms has a standard deviation. So algebraically, it's far more involved, but eventually you get the things straight. These are the exact results for that Hamiltonian in quadratic expansion. They depend on the interface potential, the sum of the surface tensions, and my lattice free energy. Okay? Never mind. So the issue is as follows. How could I analyze this spectrum? I could do an experiment. from a scattering experiment, I can get right away these amplitudes in Fourier space. That's what glancing angle X-ray spectroscopy is about, to get the surface Fourier modes. Okay? And what I'm going to do is, instead of analyzing the surface Fourier modes, I am going to introduce this quantity, which is essentially the inverse of the surface Fourier modes multiplied by q squared. And this is actually a wave vector dependent surface tension. It's an abstract concept. It has the units of surface tension. I call it wave vector dependent surface tension. Why do I call it wave vector dependent surface tension? Because in the limit of q0, this quantity is exactly the surface tension of the interface. Okay? I can show that explicitly for rough surfaces. Okay, so why does that matter? Because by studying these surface fluctuations, I can tell right away whether my surface is smooth or not. If the lattice parameter is different from 0, I am in a smooth interface, and then this wave vector dependent surface tension looks like this. Recall, I have two surface tensions in my pre-melting film. The one that corresponds to the fluctuations of the solid liquid surface, and the one that corresponds to the fluctuations of the liquid vapor surface. Okay? My pre-melting film is bounded by two surfaces. So this is the solid surface, this is the liquid surface, and these are the cross correlations. This has no clear interpretation. They diverge. However, if W becomes 0 at the roughening transition, this is the renormalized value of W. If W becomes 0 at the roughening transition, then the wave vector dependent surface tension changes completely. They now all converge to one single value. And what is that single value? It's the sum of the solid liquid and liquid vapor surface tensions. Okay? So
here you assume that you have solid liquid surface tension independent on the crystal orientation?
It does depend on the crystal orientation. Okay, but I haven't introduced that dependency. But that would be an additional complication to take into account.
Perhaps it's more or less the same question. So when W is different from 0, the minimum of gamma, does it correspond to the crystal spacing? Do we have kind of resonance between the Q of the fluctuation and the...
I'm not sure, but likely yes, there is some implication on the wavelength where this minimum occurs, okay? But I haven't worked out what that actually means, okay? But the important thing to take away, if you didn't follow me yet, never mind, is we can have either smooth or rough interfaces, and the fingerprint of that transition is the behavior of the wave-dependent surface tensions. Never mind if you didn't follow the maths. If you are smooth, my wave vector dependent surface tension will diverge. It makes sense. I said the wave vector dependent surface tension is a surface tension. If you are smooth, your surface tension, that is the likelihood that you can bend an infinitely long surface, is infinite. You cannot bend it. It's smooth. You cannot bend this at long wavelengths. Perhaps you could look at small wavelengths and see some bumpiness. But for the whole bench, it's flat. So you cannot bend it. So your surface tension becomes infinite. So the surface tension of ordinary smooth solids is infinite for large-scale deformation. If you are a fluid interface, you can deform always, very easily. And the cost of deforming is just a finite surface tension. Okay? So what that says is that when eventually you become fully rough, then your pre-melting film is behaving just like a fluid interface in which these two surfaces fluctuate. They are coupled. In the long distance, they are coupled. And it behaves like a single effective interface with a surface tension that is the sum of both surface tensions. So that makes sense. Okay. It looks complicated. So I think I'm going to skip this part where I show how to find out exactly the roughening transition. You can do the maths, and eventually what you get is a self-consistent equation. Okay? you can get a Hamiltonian which is fully quadratic in terms of W, the lattice parameter, but actually the lattice parameter is a renormalized lattice parameter. It's the one you'd get in the quadratic expansion times a factor that depends on the surface fluctuations. But the surface fluctuations themselves depend on W. And here you have a feedback. You have a self-consistent equation, and it's amazing, but it can be solved analytically. Okay? So you get the Raffanin transition. Never mind. Here I show how you'd get the Raffanin transition, but we can skip that because it's tough. And we go to our second conclusion. If you are a solid-liquid interface, you have a Raffanin transition which is dictated by your surface tension. But if you are a pre-melted interface, your Raffanin transition will be dictated by the sum of the two surface tensions. What does that mean? That for the pre-melted film, the Raffanin transition is always above that you'd get for the solid-liquid interface. Recall that a pre-melted film is solid, a little bit of liquid, and then vapor. And I compare that with a solid and a liquid. The Raffanin transition of the pre-melted film is always above, because it's dictated by the sum of the two surface tensions pertaining to the pre-melting film, rather than just to one of them. Okay? So eventually, what this means is that indeed, we can have, well, the issue is, could we have steps? Could we have steps in a system that is pre-melted? That takes us back to our first question. Could we have steps in a surface that is pre-melted? My model is saying, yes, we can. Because I'm showing that a system that has a pre-melting film shows the Raffanin transition. So first you have the pre-melting film, then you have the Raffanin. And here, this is occurring before the Raffanin transition. Why can I tell it's before the Raffanin transition? Because I can see the steps. So it can be pre-melted. Okay? So let's continue. Can we now test this theory in real world? Well, we could, but I'm doing it in virtual world. So I don't do the experiments, but I can do the computer simulations. Now I'm going to test this phenomenology using my computer simulations. Recall that what I will do in computer simulations is simply to study how my surface fluctuates. From the position of the atoms in my simulations, I can tell what is the surface height and calculate the Fourier modes of those surface heights and square them. And from that, I get a wave vector dependent surface tension. Okay? So let's see what happens. Okay, I'm going to start with an easy interface. This is the liquid vapor system. Okay, this is a bulk slab of liquid, and on top of it, it's vapor. It's vacuum essentially, and I have a realization of the disorder. Okay, and I make many such snapshots and get my surface fluctuations. And from my surface fluctuations, I get the wave vector dependent surface tension. It looks like this. It's converging to a value because I am at a fluid interface, which is rough. Okay? And one can test that by fitting these to the expectations, this extrapolates at Q0 to a value that is exactly the surface tension of my model. I can test that independently. Okay? So it works. Now let us consider the other interface that is involved in my system. This is a solid in coexistence with a liquid. Okay? This is not a pre-melting film. I have periodic boundary conditions, so this is a solid in coexistence with a bulk liquid. Okay? But still I have surface fluctuations, and you might not have not expected this, but look at them. The amplitude is very large. It's very large because from this wave vector dependent surface tension, I can see that this interface is rough. It's not smooth. It's rough. It doesn't behave in a way significantly different from this one. It actually has a smaller surface tension. So the amplitude of the fluctuations are larger. Okay, so that's for the two bulk phases. The interfaces separate in two bulk phases. Now I do the simulations for my system, which is bulk solid, in coexistence with bulk vapor. And I get a pre-melting film. And all I've been doing is describing this pre-melting film in terms of the properties of this surface and this surface, the bulk ones that are easier to understand. Okay? Here I study the surface fluctuations of this surface, the one separating solid from film, and of this surface, the one separating film from vapor. Okay? And when I do that, I get this for the film vapor fluctuations, and I get this from the film solid fluctuations. So there's one first extraordinary thing, is that they very much resemble up to some wave vector. Okay? Up to some wave vector, they're very much the same. So at small length scales, my pre-melting films behave exactly as the bulk interfaces. Okay? Second, what you can see here is that I am converging to a finite value. Okay? So this prism phase at -2 Kelvin, it's a rough interface. This is known in experiment. Prism phase, very close to the triple point, are rough. Okay? And here I have plotted also the cross correlations. They all converge. Yes.
I have a question, but so I was just about to ask that here in your simulation, the solid looks almost of the same thickness as the pre-melting.
Yes.
So does it matter that you don't have a solid which is
well,
larger?
In simulations, conceptually, you always have the problem that your system is of finite size. Yeah. In practice, we now have sufficient experience that we know when that limit can be ignored. So it's not really important. It could perhaps affect properties at 0.5% or whatever. Huh? It is true, yeah. Okay, now let's do the same thing, but at -8 Kelvin. The same surface, the prism phase, at -8 Kelvin. When I do that, these are my surface tensions for this state and this state, so liquid vapor and solid liquid surface. They are still smooth, but if I study my system now, notice it has a pre-melting film thickness much smaller. The amplitude of the fluctuations looks smaller, don't they? So when I plot the spectrum of my fluctuations, look what's happening. Is this not diverging? Okay, so here I have a roughening transition. At high temperature, my prism phase was rough. At low temperature, it looks smooth. Okay, so I do have the roughening transition in the prism phase of ice. I've shown that. Okay, and in fact, if I take the results at -2 and at -8, these simulation results can be roughly well fitted by my model. At -2, they were very well fitted, and at -8, they are not quantitatively fitted, but qualitatively they do get the fit. So this seems to confirm the theory. Okay?
Wait.
Yes, go ahead.
It's diverging, and I thought this was a sign of the roughness.
No, you get this converging, all of the surface tensions converging to a value when you are rough, and they diverge when you are smooth. Okay?
And how do you prescribe in the simulation that you have the prism basal phase?
Well, I just prepare the lattice with the right orientation.
Okay.
I just prepare the lattice such that the vacuum that is exposed to the ice slab is in the right orientation. Okay, so second conclusion, which is the confirmation of computer simulations of my previous conclusion. Indeed, I can have pre-melted surfaces that are smooth, and there is a roughening transition between them. Okay, so there's no problem in observing steps in a surface that is pre-melted. Okay, perfect. Now, what I'm going to do is to use this analysis to study the problem, perhaps in a more transparent way. This is my pre-melting film. That thing in between these two lines. And I have fluctuations. So what I'm going to do is to define the surface fluctuations. That's actually what I have been Fourier transforming. That is the surface fluctuations of the liquid vapor surface and the surface fluctuations of the solid liquid surface or ice film, film vapor. But instead of doing Fourier modes, which might be confusing, what I'm going to do is to plot the probability of observing a given fluctuation in real space. Now it's real space. So I calculate surface fluctuations about the average value of the surface and plot what is the likelihood of observing such fluctuations. Okay?
I have a question. All the fluctuations you are studying are in space, and you don't speak at all about dynamics.
Not yet.
Yeah, because we could ask the question, probability to see this fluctuation in a certain amount of time?
Yes.
Dynamics is going down.
Of course. You could study instead of the static spectrum of fluctuations, the dynamic spectrum of fluctuations. I'm currently working on that, actually. Okay? And this is what we get. Okay? Let's concentrate just on this column. Here is the study of surface height fluctuations for the basal facet, the one on top of my prism, as a function of different temperatures. Okay? So at very low temperature, the distribution of surface height fluctuations is an arrow Gaussian. That makes sense. At low temperatures, I have a smooth surface. The fluctuations are small and Gaussian. That's not unexpected. But look what happens at minus 32 degrees. My Gaussian distribution starts becoming very clearly a bimodal distribution of both surface heights. Okay? I'm plotting in blue the solid liquid surface of my pre-melting film, and in red the liquid vapor surface of my pre-melting film. They become bimodal. And eventually, if I increase the temperature, unexpectedly they become unimodal again. So I can say that as I increase the temperature from minus 82 to minus 2 degrees, I go across one and then two phase transitions, because the distribution of the order parameter is completely different. So what these simulations revealed is that the basal surface undergoes two surface phase transitions. I have one phase which is Gaussian, another which is bimodal, another which is Gaussian. Okay, so that's interesting. And what is the significance of this bimodality? Here, what I'm showing you are snapshots of it's a contour map. It's a contour map of the surface heights. When I am in this bimodal region, my surface, this is real space contour map. My surface, what shows is correlated up and down steps. This is a terrace up, this is a terrace down, terrace up, terrace down. I get large correlations of steps that are formed. Okay? And that had been predicted in some 1990 paper that received very little attention. The possibility of this kind of transition. It's called, well, never mind. Okay? Interesting. Now let's study the prism facet, which is the other one involved in my ice crystals. Okay? I have studied the same thing for the prism facet, and look, I get similar kind of transitions. Here I have a very narrow Gaussian distribution, and then when I reach minus 32 degrees, it's almost bimodal. But when I increase the temperature, it becomes unimodal again, and eventually it broadens very much. A Gaussian that is broadened very much is what I can expect when I am close to a roughening transition. So this is the transitions that I was expecting when I started this work. But in the meantime, I actually observed these unexpected transitions from Gaussian to bimodal and from bimodal to Gaussian. Okay? So what this says is that both the basal and the prism facet undergo two surface phase transitions as you heat them up from minus 200 Kelvin to about the melting point. Okay? So this is the situation. For the basal phase, it seems I have from low to high temperature, three different phases. And for the prism phase, I also have three different phases that are similar, but the transitions occur at different temperatures. Okay? And I expect that at each phase transition, the growth mechanism will change. Okay? So I can expect non-monotonous changes in the growth rates. And isn't this appealing in order to explain this? It is a big hint that the reason you get these changes of habits is because there are surface phase transitions on top of the ice surface, which occur at different temperatures on the basal and prism facet. Okay? So I think that's a nice thing. And it seems that with our analysis of surface fluctuations on basal and prism facets, reveal a temperature-driven sequence of surface phase transitions. And so the conjecture is, could this correlate with the plate column habit transitions? And a major question that I was asked the other day, actually. How representative is this description of the equilibrium surface structure for the out of equilibrium growth that actually occurs in the atmosphere? Okay? So that's the next part of the lecture. How well I'm doing on time?
20 minutes.
20 minutes? I think I can do it. Okay. Okay, what is this about? Yes. I have described this behavior. So at low saturation, I get the smooth surface with steps. Eventually, I get droplets. If I keep increasing the pressure, eventually I can get some kind of instability. Because below the droplet, another film emerges. That's another reason why these authors thought that pre-melting doesn't exist. They could see from their pictures that this clearly is a liquid film. So they said, okay, at equilibrium there is no pre-melting. Pre-melting only emerges at sufficiently high saturation. And they thought, this must be the pre-melting. Okay? But anyhow, the situation is that they could map their behavior on the surface phase diagram. Okay? There is this broad region in which they just see a smooth surface. They would claim it's the bare eye surface. I claim that there's a pre-melting film on top of it. The matter of fact is they do see that eventually when you cross this red line, when you cross the red line, you get droplets. And there is one curious thing here occurring. The droplets only appear well above the saturation of the metastable prolongation of the liquid vapor line. Droplets typically you would expect would appear right there, but actually they appear at a much higher saturation. Okay? And then eventually, if they cross this blue line, they get the instabilities. Okay? This state. So how could I explain this? And let's see. If I have a pre-melting film, the mechanism of growth is complex. How is the pre-melting film thickness going to evolve? It evolves for two reasons. At this surface, I have condensation and evaporation events, which will shrink or make the film grow. At this other surface, I have freezing and melting events. And I want to describe that. But I'm not very good at doing out of equilibrium phenomena. Okay? So I do it in the way that is most simple. Consider first the equilibrium state of the system, or at least the thermodynamic description. I am going to be saturated. Okay? So I am going to be at, say, this point. What has happened when I have gone to this point? That I have moved from the points I was discussing on Monday. On Monday, I was just doing the simple thing of moving along the sublimation line. And then my free energy depended just on film thickness and had these three terms. This is the interface potential. And this term. Recall what was the role of this term. This term was telling us what is the cost of making a liquid film at this point. It was dictated by the distance from this other line. The cost of making a liquid at this point is the distance to that line, because that's the line where the liquid is as happy as the vapor. Okay? But now I'm moving away from the line. So now not only one surface is in a metastable situation, also the ice now is preferred over the vapor. So I need to add a new term. How do I penalize the solid over the liquid, or the liquid against the solid, once I've moved away from that line? It's by this term. Okay? Don't have time to work it out, but if you look at my lecture notes on Monday, it's just a little bit of additional complication to write down the free energy budget of this system. Instead of 2 bulk phases, I have 3. The other day we studied an inner substrate, a pre-melting film, and the vapor. Now I need to account for the fact that this also depends on the thermodynamic state. Okay? I get this free energy, and the simple mind of doing non-equilibrium physics, when you are good at thermodynamics but not at non-equilibrium, is assuming that the dynamics is driven by free energy deviations from the equilibrium value. So I have my simple model free energy, and I say, okay, the rate at which the solid liquid surface evolves is a gradient of the free energy with respect to the position of the solid liquid surface. That's a very general principle in out of equilibrium physics. Okay? That rates of growth are gradients of free energies. If you are equilibrium, there is no gradient in the free energy and you don't grow. Okay? But if you are out from equilibrium, that is, if this field is not zero, then you get growth. Okay? And the same for the liquid vapor surface. I presume that the liquid vapor surface is going to evolve as a function of the gradient of the free energy with respect to the position of the liquid vapor surface.
Are the P's supposed to be pressures?
Yes, they're pressures. Okay? And that's the rate of growth of the surfaces. But now, how do the molecules evolve? This is number of solid molecules evolving in the system. It will be dictated by the number of molecules that freeze. You have a pre-melting film. The number of molecules in the pre-melting film that freeze will dictate you how does the number of solid molecules increases. That's very plain. Now, for the liquid molecules, it's more tricky because liquid molecules can grow because you have vapor deposition on top of the pre-melting film, or because you have melting of the pre-melting film, of the solid. If the solid melts, your pre-melting film thickness increases, so the amount of liquid molecules increases. So here I have two terms. Now I consider mass balance. This is a plain mass balance. Total number of solid atoms will be dictated by the height of the solid surface. Total number of liquid atoms will be dictated by the thickness of the pre-melting film. Plug this into these equations together with this, and it's a simple exercise to get these equations. This is the rate of growth of the solid liquid surface. This is the rate of freezing. And this is the equation for the evolution of the film thickness. Okay? So now I have a set of two coupled differential equations. Why am I doing this? I want to know whether my study of equilibrium surface fluctuations is representative of the growth of the system. So my rationale is as follows. If the pre-melting film is at all relevant for understanding the way ice grows, there must be some special regime here that I call the quasi-stationary regime, in which ice is freezing at a finite rate, but the pre-melting film thickness remains constant. Okay? And if this holds, then I'm entitled to say, of course, my equilibrium structure should be representative of the way ice grows. And you can easily work out from these equations that this holds, provided this condition is obeyed. Can somebody recognize this condition from my lecture on Monday? Disjoining pressure. In my lecture in Monday, I said, what is the equilibrium condition of the pre-melting film? How do you determine the film thickness? It was by an equation completely analogous to this one. Disjoining pressure was equal to a difference in pressure. In that case, this difference of pressure was a purely thermodynamic quantity. But now I am doing out of equilibrium phenomena, and I have replaced delta P by delta P sub K because this is a kinetic pressure difference. Look at it. It's a weighted average of the thermodynamic fields that drive the system out of equilibrium times the kinetic coefficients in the equations. Okay? So it's really a beautiful equation because it's the way to extend the thermodynamic theory in a very simple way to describe the dynamics.
So the H we obtain by those kind of analysis can never be the equilibrium H we use, for example, at the beginning of your lecture, because at that one, the derivative of G is null and P is 0.
I didn't get the question, but because I'm a little bit behind, we can discuss it afterwards, okay? Because I feel that I'm very tight on time, okay? So the good thing is now I can search, look, this depends on temperature and pressure. So what I can do is as follows. Recall that in conditions of equilibrium, my free energy is interface potential less delta P times H. So I extend that concept to out of equilibrium. So this is, in mathematical jargon, I think this is a Lyapunov energy or something, okay? It's the extension of the equilibrium concept to out of equilibrium. Instead of putting the equilibrium delta P, I get the kinetic delta P. And when I do that, I get these three kinds of free energies, depending on the value of delta P. If delta P is negative, then I get my interface potential plus a straight line with positive slope. I get this. So this is the situation where I am always externalizing my pre-melting film thickness at a finite value. Then I get a regime of growth in which ice is growing and you have a pre-melting film of finite thickness. And that occurs at this red line. I can solve that from my equation for the overpressure. Okay? By solving this equation, I can get this line. It's equivalent to a Clausius-Capeyron equation weighted by kinetic coefficients. Okay? Now, eventually, if my pressure becomes positive, this delta P pressure becomes positive, I am subtracting to the interface potential a straight line with negative slope. So my free energy is going to look like this. I will have a finite thickness that can be equilibrated, but it's metastable. The system likes to go to infinite thickness. And that's exactly the way free energies look when you get liquid droplets. Okay? You have a region where the pre-melting film is metastable and can be stabilized, but water wants to condense in the form of a droplet and keep growing as a big droplet. Okay? And that occurs exactly at this line. And eventually, if delta P is sufficiently large, then my free energy is this negative slope line is sufficiently large that my minimum vanishes and I get instabilities. And I get the instabilities observed in experiment. Okay? So I think this explains the experimental observations. Just very briefly tell you that this theory is the plain and simple theory that can be done just from bare thermodynamics and little out of equilibrium concepts. You can extend that with my Hamiltonian. I have a Hamiltonian that allows for inhomogeneities. I have a Hamiltonian that allows for inhomogeneities, and you can extend that in a very much more complicated way that I don't have time to describe. And then you have the full theory for describing the inhomogeneities. Okay? Let me show you one film because it's fun. Okay? If I, in this situation, and I create a small step, this situation is below the red line. So my free energy looks like this, which means that I am always stable at a film of finite thickness. Okay? Oh, this doesn't work. I need to. Is it working? Ah, good. It's not working. Ah, fair. You see? Yeah, I stopped. Oh, so okay. So what first happens is this red line is the solid surface. The blue line is the liquid surface of my pre-melting film. So what I've seen is that first a step is nucleated on the surface and then it's propagated horizontally. That's exactly what I claim the people in the experiments are observing. They do observe steps, they translate, but it's the liquid on top of the steps that is translating. Okay? Then I have, for example, if you are at above the stability limit, then you'll get the same step and you will form the same thing, but then eventually it becomes wild. Okay? Okay. I have very nice films, but no time to show them. Okay. So, quasi-stationary states of crystal growth with constant pre-melting thickness can exist. And this means that my equilibrium study is good to understanding the pre-melting, the growth of crystals. And this takes me to how crystals grow. Okay? I'm not going to spend much time, but I have already said that first you need to form a step, and that's an activated process. Because if you want to form a step, you need many molecules to arrive at the same position and decide they want to grow. So that's unlikely. And it costs you a free energy. Creating this step costs you a free energy. And the good thing is that from my model, using the same arguments I described at the beginning, I can get the cost of creating a step free Beta is the step free energy. Is the cost of creating a step. And this free energy depends on my parameter W. The one that was describing the cost of creating lattice defects. Okay? So if I want to calculate step-free energies, I just need to know what is the W value of my parameter of the lattice. In the sine Gordon potential, I have this W parameter. Okay, so recall that in my simulations I could get these real space distributions, but I can also get the wave vector dependent surface tensions. And I can fit these wave vector dependent surface tensions to my model. And by fitting the simulation results to my model, I get the parameters. Okay? And they work well. For example, for this distribution, my model gives a very nice fit. And from the model, I get the value of W. And if I know W, I can measure the step-free energy. Okay? The larger the step-free energy is, the slower the crystal grows. So now what I'm going to do is to show you the results for the step-free energies that I get as a function of temperature. Okay? These are experimental results by Ken Liebrecht. They were most likely shown at this school 3 years ago. Okay? These are the results you get from simulation. Okay? The blue line corresponds to the basal surface. It's step-free energies of the basal surface. The red line is the step-free energies for the Prince phase. Okay? So look, at high temperature, I have a step-free energy for the basal phase, which is large, and a step-free energy for the Prince phase, which is small. The crystal grows faster if the step-free energy is smaller. So at low temperature, I have my Prince growing along the sides. Then at this temperature, I get a crossover. And then the step-free energies of the Prince phase are larger than those of the basal phase. Okay? Which means that the basal phase is going to grow faster. Okay? And then I have yet another crossover. Another crossover, and my Prince phases get to grow faster. And likely, well, here I don't have quite a neat crossover. So I'm not being able to explain this very neatly. It's the less clear transition actually observed experimentally. But I can see the crossover of growth loss for the first 3 transitions. Okay? So I think that's a nice explanation of the Nakaya diagram. Here you have it. You have the same kind of transitions. Nakaya had a very beautiful sentence that has become memorable. Snowflakes are letters sent from the sky. Why? Because by the shape of the snowflakes, you can tell what was the temperature and humidity at the atmosphere. 1 kilometer above. Okay? So with conclusion 6, I hope I have shown that equilibrium surface structure and pre-melting behavior explain the crystal habit crossovers of the Nakaya diagram. Okay? Still, it's a hypothesis, but it's one that seems to be consistent. Nobody has seen the pre-melting films at atomic resolution. Okay, so let me thank my co-authors, because it has been joint work with several authors from results of last talk and today's lecture. And let me thank you for your attention.